Hello students, today we will do the torque on a current loop and magnetic dipole. Now this topic 4.10 have different part. The first part is torque on a rectangular loop in a uniform magnetic field. So we have a rectangular loop ABCD which is placed in a non-uniform magnetic field B. So let us see the situation. ABCD is a rectangular loop where we have its length AB is equal to CD is equal to B, that is denoted by B, either you say it a length or a breadth, and BC is equal to AD is equal to A. So this is the length and the breadth. Here the magnetic field is uniform, so a rectangular loop placed in uniform magnetic field, that is B vector, which is along the x-axis. So this is the direction of the magnetic field intensity. Now this rectangular loop is connected to a battery of V volt. This is a ring, a half ring. So we will see that this coil will rotate and this end AB will come to this side and CD will come to this side, depending upon the rotation, whether it is a half rotation or a full rotation. If it is a full rotation, AB will come back to its original position. We will also see how this rectangular loop will rotate. So these are the two rings which are connected to the rectangular loop, and these are the two brushes through which the current is sent through the rectangular loop. So these are two brushes which are fixed and the rings are connected with the rectangular loop. So this ring just touches the brushes. They are not connected. They touch each other because this rectangular loop will rotate due to torque acting on it. So now this is the situation. Also, we assume that the loop, that is a rectangular loop, is placed along the magnetic field. The loop is placed along the magnetic field. So if the loop is placed along a magnetic field, its area vector is perpendicular. So let us assume that this is a loop. So this is end A, this is B, this is C, and this end is D. And this side is a north pole. So let us assume this wall, this side, right hand side is a north pole and the left hand side is a south pole. So we have a uniform magnetic field along the x-axis. The loop is placed parallel to the magnetic field. So magnetic field is along the x-axis and the plane of the loop is also parallel to it. It means its area vector. So its area vector, you can take a area vector either along the y-axis or along the negative y-axis. The area vector is perpendicular. So loop is placed either you say parallel or along the magnetic field. So this is the situation. Then from these two ends, this loop is not complete. We take two ends outside and connect it with the brushes, touch it with the brushes, and these two ends have a ring-like structure. So the current will be sent in the loop. Now the current will flow in this direction, that is, in this loop the current will flow from A to B, B to C, then C to D, and then again it comes out from D. So this is the direction of the current in the circuit. So if we take this loop, so this side is north side and this side is a south side. So that is a magnetic field is along x-axis. So current is flowing from A, B, C, D, A. Let us try to understand by taking the complete loop. So if I see from the top, the current flowing is in a clockwise direction. This is my end A, B, C, D. So the current is flowing clockwise. The current is flowing clockwise. Now, if it is flowing clockwise, this should be the south pole and this should be the north pole. If the current is flowing, we know that a current carrying loop, whether it is a circular loop or a rectangular loop, it behaves like a magnet. We will come to that point. Now let us find out, when we send a current, it is like the four wires AB, BC, CD and DA, that is the four wires, are placed in a uniform magnetic field. And we know that when a wire carrying current is placed in a magnetic field, force act on it. And what is the formula for the force acting on it? So force acting on loops or force acting on the side of loop is found by formula F is equal to IL cross B vector. This is the formula that we know. So we will try to apply the force on wire AB, wire BC, wire CD and wire DA. Now let us use this formula. So the length side, that is inward. The length side is inward. Let us take IJK, a unit vector, so you will understand the direction of the force. Now before we take this two and AB and CD, let us first take BC and AD. Now current is along BC. Current is along BC. If the current is along BC, the DL vector is also along the BC, because when we take this force, we divide this into small elements and then we do the integration. So what will be the angle between L vector and the B vector? So they are in the same direction. Theta is 0. So there will be no force acting on the side BC. And if I take a side DA, this much or entire side DA, then angle between the magnetic field and DL is 180 degree. Sin 180 is again 0. So if I apply this formula, no force acts on side BC and side DC. So there are no forces acting on these two sides. So on this side, left is AB and BC. Sorry, AB and CD. Now let us see the side AB. So L is inward. Let us take this direction as minus K. I can also apply directly the cross product, but it will be easier if I use the term IJK. So L is minus KK. B we have taken along the x-axis. So it is K cross I. K cross I is J. We have a minus sign. So it will be minus J. So the force acting on this AB is in the downward direction. The force acting on this side is in the downward direction. So I either take the help of a unit vector or I can take the help of a screw rule. So DL or L is inward. The magnetic field is along the x-axis like this. This DL is inward or length is taken inward. Now I keep a screw here I have to rotate a screw in the direction from L to B, or I can also use a thumb rule. So I call my finger from L to B, thumb is downward, the force is downward. So either you keep a screw perpendicular to this plane, rotate it in the direction from L to B, so screw will go inward. If I keep the diagram like this, actually it is like this. So the force will be downward. So the force acting on the side AB, or we also called as a arm AB, is downward. Now if it is in the downward direction, for CD the current is opposite. For CD the current becomes K, so it becomes J. So what will be the current in the arm or side CD? Upward, and here it will be downward. So force is perpendicular to L and B, and we know that F is always perpendicular to L and B. There may be angle between L vector and the B vector. Here the angle between the L and B is also 90. So sin 90 is 1. So there are the two forces acting on the side AB and CD. So let F1 vector be the force acting on arm AB, and it is downward, and F2 is force acting on arm CD in upward direction. As far as magnitude is concerned, both have an angle 90. L vector and B vector in both the sides is 90 degrees. Sin 90 is 1. So the magnitude will be BIL. B-I-L. BIL. So the magnitude will be equal to BIL. This is the force, the direction of the force acting on the two wires. Now what is length here? In the length of this wire is B. So instead of L, I will write this length as small b. So we have the length of arm AB and CD to be B. Now both these forces are equal in magnitude and opposite in direction. So both F1 vector and F2 vector are equal in magnitude, but opposite in direction. That is, F1 vector is equal to minus F2 vector. Also, mode of F1 is equal to mode of F2 is equal to I. In the place of L, we have taken the length S, or it is denoted by B. So I will write it as IB into B. So this is the magnitude of force. Now both the forces, one force is upward and another force is downward. So the magnitude of both the forces IBB. Direction is opposite. So what is the conclusion? The resultant force or net force is 0. So F net is equal to 0. Clearly F1 plus F2 is equal to 0. So that there is no resultant force acting on this loop. So now we will view this coil from this side AD. So I am viewing like this. So this force is upward, this force is downward. I am viewing from this side, that is from side AD, and I will draw the diagram. This is my AD portion. Now if I take this portion as AD, my force is on this side is upward, that is F1. This is downward, that is F2. So F1 is F1 is this, that is downward, this is F2. So their magnitude is same. So this is the force. I am viewing from the side AD. The length of this side is A. The length of this side is A. So if I take this midpoint, this entire side is A. It can be written as A by 2, A by 2. I take this point. This is my point D, and this is my point A. The magnetic field. We talk about the magnetic field. The magnetic field is along the x-axis. Now, we are going to define a new term which is called as a magnetic moment. We have a new term which will be defined as a magnetic moment, similar to an electric dipole moment. So, let us say the new terminology and its meaning. So this is the situation. First we complete this portion. This is midpoint. So notebook is kept like this, or this is a rectangular loop. This is north pole here. This is south. Magnetic field line is from north to south. So we found that the force acting is upward and another force is acting downward. Their magnitude is same. So the resultant comes out to be 0. But if I see both the forces are separated by a perpendicular distance, this is a perpendicular distance between the two forces. So they are separated by the perpendicular distance. So if you remember, if the two forces are separated by a perpendicular distance, they behave like a couple. So it is like this. One person is pulling this side upward and another person is pulling this side downward. There is no force on this side. So what will happen? There will be no linear displacement. But this coil will start rotating. So this will be the rotation. That is, if I see from the side AD, the rotation is anti-clockwise direction. So this is how it starts rotating with the angular velocity omega. So when a rectangular coil is placed in a uniform magnetic field, the resultant force acting on it is 0. But there are two forces which are acting on the two arms in an opposite direction. Now this is the situation when we have assumed coil to be parallel to the magnetic field. But we will see as it start rotating, it should rotate now because it behaves like a couple. So there is a torque acting on it. So it start rotating. Now if I take an area vector, we will define a new term, magnetic moment. Now if I take, suppose this is an area vector. So what is angle between the magnetic field and area vector? 90. But let us take area vector in the downward direction. Now if I start rotating this coil, what will happen? The angle, this area vector will remain perpendicular to the surface, perpendicular to the coil. Magnetic field is fixed along x-axis. So when the coil start rotating, the angle between this, for the time being we call it a area vector, which is 90, will start decreasing. But we will discuss this case when it starts its rotation. First we find out the torque acting, because both the forces are separated by a perpendicular distance. Also, if I extend this line, this is called line of action of force. So both the line of action of forces are separated by a perpendicular distance. And whenever there are two forces whose line of actions are separated by a perpendicular distance, a constant or fixed perpendicular distance, it behaves like a couple and the torque act on it. That we have studied in 11th. So here torque act on a loop. Now how will you find out the torque? If I use a term couple, then the torque is defined as the magnitude of either force and the perpendicular distance between the two line of action of forces. So what is the perpendicular distance? That is A. That is A. So directly if I say that torque act on a loop and loop behave like couple, then the torque was defined as the magnitude of either force. So I write either F1 or F2 into perpendicular distance between two line of action of force. Let me write this as two forces, between the two forces. So what is the magnitude of force? That is IBB. What is the perpendicular distance? So total perpendicular distance is A. So tau can be written as length into breadth. That is the area. So capital A is equal to area of loop. This is the term, tau formula. That is BAI. If I have n turns, then I multiply this by n. So if there are n turns, then I multiply it by this, and to remember the formula, I write a name Bina. So if there are n turns, we have taken only a rectangular loop having one turn only, but this is the case when there are n turns. Now either you directly apply this formula, or tau can be written as tau1 plus tau2, that is torque produced due to F1, torque produced due to F2. Now if you remember this formula, that is R cross F1 plus R cross F2. Now what is R here? That is A by 2. So I extend this. This is like in 11th we call this R as a position vector or the distance from the center. So it was extended, angle becomes 90, sin 90 becomes 1. So instead of R, I write A by 2 F1. Again F1 is IBB. Then tau2, that can be written as R vector cross F vector. I extend this. This is my A by 2. This becomes 90 degree, sin 91. In the place of R, I write A by 2. In the place of F2, I write IBB. So I am writing this in a scalar form. So actually it should be a vector. Then we write a magnitude. So again, if I add these two terms, it comes out to be tau is equal to IBBA or IAB. So this is the torque acting on a rectangular loop. When the loop is assumed to be parallel to the magnetic field. So surface is parallel to the magnetic field. So torque will act, and now it will start its rotation. It will start its rotation. So here, what will be the direction of the area vector? So if I want to find out the direction of the area vector, again I can make a use of right hand rule. Now there is two possibility. Either you can take a vector in the upward direction or a vector in the downward direction. Now if I take it in an upward direction and this as a downward direction, there will be a change of a sign, plus or minus. So we have a convention. We rotate a screw in the direction of the current. So if I keep a right screw and rotate it in a clockwise direction, the current is flowing clockwise. So if I rotate this as clockwise, I found that the screw will go downward. I will find out that the screw will go downward. So this is your area vector. So it makes an angle 90 degree with a B vector. So this is how we determine the direction of the area vector with the help of a screw rule. Now let us define a new terminology which is called the magnetic dipole. So like we have an electric dipole. What was electric dipole? Electric dipole was a system of two equal and opposite charges separated by a finite distance. Here in the place of the two charges, we have the two poles, that is north and south pole. We know that they are separated by a finite distance. So we will also find out, or we will study in detail, the magnetic dipole of a bar magnet. But here we are dealing with a loop. So we have already studied this, that if a current is flowing in a circular loop or rectangular loop, but we have studied this. If the current is flowing in a clockwise direction, then this phase acts as a south pole. And if the current is flowing in an anti-clockwise direction, then it behaves like a north pole. We know this. Now we did the theory also, where we have taken the loop along the YZ plane. The current was flowing anti-clockwise and we found the magnetic field intensity along its axis. And we have also drawn the magnetic field lines of this. So the magnetic field lines of this comes out to be like this. We know that it behaves like a bar magnet. So we have studied all this in the previous lecture. This behaves like a bar magnet and the field lines is like this. This is north and inside it is from south to north. So this was the situation. This is how the magnetic field is formed. Now if you remember, the direction of the electric dipole moment was from negative charge to positive. So whatever role is played by the negative charge there, here that same role will be played by south pole and positive as a north. So the direction of the magnetic dipole moment is from south to north. The direction is from south to north. So the direction of the dipole moment is from south to north. And the magnetic dipole moment for a bar magnet will be denoted by small m. So there in the first chapter we denote it by a P. Here we will denote the magnetic dipole moment by m. So again it is a vector quantity. The direction is from south to north. And if a loop carry a current, then the magnetic moment is given by the formula I into A vector. We will come to this formula in the next chapter. In detail we will discuss about it. So for the time being, the magnetic moment of a loop, any loop carrying current, is given by I into A vector. Now whatever is the direction of A vector, that is the direction of M vector. So either you find out the direction of A vector, it should be the direction of the M vector, or as I said, its direction should be from south to north. So see the direction of current. Current is flowing from A, B, C, D. So this is how we kept the book, A, B, C, D. So current was flowing clockwise. So this is south and this is north. So what will happen? The magnetic field lines will be from north to south and then south to inward. Magnetic field lines originate from north, goes to south, inside it is from south to north. So magnetic moment is from south to north. So here we have this upper end behaving as a south and this as a north. So the magnetic moment should be in the downward direction. But either you remember like this, south to north, or you apply the thumb rule. You see, this thumb rule is used to find out the direction of the magnetic field intensity in Ampere circuital law. It gives you the direction or the convention for the current, which current should be taken, positive or negative. And now it also helps to find out the direction of the magnetic moment. So it has many uses. So I take my right hand, I curl my fingers in the direction of the current, or I will curl my fingers in the sense the current is flowing in the loop. So here the current flowing is in the clockwise direction. So I curl my fingers clockwise. My thumbs comes down. This thumb, either you say it gives a direction of the area vector or a magnetic moment. If the current is flowing anti-clockwise, I will curl my finger anti-clockwise. Thumb will be up. So area vector should be taken upward, or you say the magnetic moment should be taken upward. So if this is the case, torque is Ia. So the another term can be M, that is Ia into B. So tau can also be written as MB, provided this is the situation when the angle is 90 degree. Now this angle will change when this coil, now it is clear, the coil will rotate anti-clockwise. So when it start rotating, that is the angle between M vector and B vector will change, and it should not be a scalar formula. This is only we are writing when this is the situation when the angle between the area vector or B vector is 90. As soon as it start rotating, this torque will also change. We will see whether this torque will increase or decrease, or what will be the correct formula. But the magnetic moment is defined as, it is a vector quantity Ia, this is area, and the unit becomes ampere meter square. You find out its dimensional formula also. So this is the case. Now we will come to a situation where this angle will not be 90 degree, but there is an angle of theta. Now this becomes M vector. So viewing from AD, now say this coil will rotate. Now if I rotate it like this, what is the angle? 90 degree. That is 1/4 rotation. AB is, this is AB, 90 degree, 180 degree, 270 degree. Again this AB comes at this point. So along this axis, so it becomes 360 degree. So what is angular displacement? Pi by 2, pi, 3 pi by 2, 2 pi. This is your angular displacement. I can find out the angular velocity also if I know the angular displacement. Now we will consider not a situation of 90, 180, 270 or 360, but a general case. So let us assume this coil, this is your AB, this coil is rotated by 30 degrees, say. Sorry, it rotates anti-clockwise. So it rotates like this. You have to view it from, the diagram should be viewed from this side AD. So earlier, this is your M vector, initially this was your B vector, that was 90 degree. This is the situation. This is your B vector and this is my M vector. This is 90 degree. This is the case. Now we know in a cross product the angle between these two terms will change, but F will always remain perpendicular to B and M. So this is your F. So it rotates. F will always be perpendicular to L. F should also be perpendicular to the B. B is also fixed. That is the rule of a cross product. Now we will view it from this side. Let us rotate it by a small angle in anti-clockwise direction. So this becomes M. This is B. So the angle will decrease. Now when the angle will decrease, we will see whether the torque will increase or decrease. What happened in that situation. Now let us assume that the coil start rotating and we know it started rotating anti-clockwise. This force was upward, this force is downward. Suppose that it rotates by a small angle and remember we are drawing the diagram when we view this coil from the side AD. So suppose earlier the angle between the magnetic moment or area vector and B vector was 90 degree. This was the diagram. Now let us assume the coil rotates by a small angle theta. So what will happen? B is fixed. It is along the x-axis. The coil will rotate. So this will be the situation. This angle will keep on decreasing. And when this coil completes 1/4 rotation, that is angular displacement is pi by 2, the area vector and the magnetic field are in the same direction. And then again it will be the situation like this, then this way and this. One complete rotation is over. So the coil will start rotating. Now there was no force on the arm CD and AD, but there were two forces acting on the arm CD and AB. Now if you assume that it rotates by a small angle theta, as a electric dipole was rotating in a uniform magnetic field, uniform electric field. So it is similar to a electric dipole. There we have a dipole. Here we have a loop, then loop itself behave like a dipole because its one face is south and other face is north. So if I view it from AD portion, this M becomes, M makes an angle theta with a B vector. So you view this diagram. Now this becomes our F2. This becomes our F1. This is a B vector. This is the direction of the magnetic field lines. And this is side A, that is the arm AD. Its length was taken as A. So this point, say this is D point, this is A point. This is the situation. And where is the M vector now? This is my M vector. It makes an angle theta. So this is the situation when we view this diagram from the side AD. Now BC and AD, say this was the, now this side BC also make an angle theta, BC and AD, but both the forces are mutually opposite and their line of action of force also coincide, but that is not the case for these two arms. So that both the forces are collinear. This force act in upward direction, this act in downward direction. We place this forces, they are collinear, and the resultant comes out to be 0. So whenever this coil start rotating, the total force contribution by these two arms will be equal in magnitude, as well both the forces are collinear. But here both the forces are non-collinear. They are separated by the perpendicular distance. So if I drop this or I extend this line, this is a line of action of force. This is line of action of force, and this is also line of action of force. So this is the situation. When we view this coil from the side, AD. So now this force, this side AD, we have rotated by small angle, so it becomes theta. This is the force, which is always perpendicular to the B vector. It should always be perpendicular to the B vector. This should also be perpendicular to the B vector, because F is equal to IL cross B. So F should be perpendicular to length and the magnetic field. So here this force are perpendicular. Now, so it should be clear that when this coil start rotating, and viewing from this side, these two forces, one will be in this direction, suppose other should be in the downward direction. Both the forces are collinear. There is no line of action of force coinciding, but if the line of action of force are not separated by a perpendicular distance, but these two forces have the line of action of forces separated by the perpendicular distance. Now if this angle is theta, this is 90 minus theta. Now what is this? A by 2. What is this side? A by 2. This angle is 90 minus theta. So this component should be A by 2. This component should be A by 2 cos 90 minus theta, that is sin theta. This side is also, this is 90 minus theta, so this is 90 minus theta. So it should be written as A by 2 sin theta. A by 2 sin theta, where theta is angle between M vector and B. So earlier, when the coil was like this length was A by 2. Now it is A by 2 sin theta. So what will happen? The torque will decrease. The force will also decrease. So again, we write this magnitude of these forces remains same, that is F1 is equal to F2 was equal to IBB. It is same, but what is here the angle is 90 degree. The F is perpendicular to B and B, so that angle is different, and this is the angle theta between M vector and the B vector. So here the magnitude still remain IBB. Again, both the forces are non-collinear and they are separated by a perpendicular distance. Now this perpendicular distance, which was earlier A by 2, now it became A by 2 sin theta. So it decreases. The torque will also decrease. Now, but still it behaves like a couple. So these two forces are same, but there is an angle theta now between M and B. These two forces, earlier they were parallel to the magnetic field. Now even if it rotate, this is downward as compared to, so it makes an angle theta this side, AD side. But if this is the direction of the force, it should be the direction of the force here. So if you consider a theta, again both these forces, if I take this side, see earlier the situation was the angle was 0, that is L was in the direction of B. Now if I rotate it in anti-clockwise direction, the angle between M and B vector decreases, and let this L and B vector increase by this small amount. Now I apply the force, so force should be perpendicular to this L and B, so this will be the case. So if this is the case, L cross B, say L cross B, suppose this side. So that if I apply the same formula there, it comes out. Both these forces comes out to be collinear. So you have to remember that force on arm BC and AD are collinear. Magnitude would be same. So resultant force is always 0. We know this in electric dipole in the uniform electric field. So there also the resultant force was 0, only the torque was acting. So resultant force here is 0, that is collinear. But F1 and F2, that is force on arm AB and CD are non-collinear. So they constitute couple. But now this torque will start decreasing. Now I have to find out again the torque formula. So tau is equal to tau 1 plus tau 2. Now what should be written? Here we have written A, so I can extend this. Again the angle between these two terms is 90 degree. So I directly write a magnitude A by 2 sin theta into the magnitude of either force, that is I by B. So F tau 1 again R1 cross F1. Angle between R1 and F1, that is 90. So this cross is gone. So tau 1 can be written as R1 F1. In the place of R1, A by 2 sin theta, F1 magnitude. Similarly, A by 2 sin theta, IBB. So torque acting on it becomes now length into breadth, that is area, half of term. So it becomes IAB sin theta. Now we have defined this torque, I into A as magnetic moment. So it becomes MB sin theta, where M is equal to IA. So this is the magnitude of the torque which decreased. So if you remember, the formula tau was equal to PE sin theta. In the place of P we have M, in the place of E we have B. The other thing remains same, that is angle. So this is the general formula. So again we wind up by revising this. So initially the coil was kept parallel to the magnetic field. Then we found that these two forces behave like a couple because they are non-collinear. In the first case there was no question of these two arms because they were parallel to the magnetic field. Now the torque act on this, it is like a dipole placed. Now torque act, so angle decreases. Now earlier the angle was 90 degree, now it becomes theta. We stop this at this point. This is your AD. We draw this diagram like this, AD. Then the force is always perpendicular to B vector. We found that these two forces behave like they constitute a couple or they form a couple because they are non-collinear. As far as that forces are concerned, for this two side, this is your L, this is your B. So again you apply this formula, one force will come on this side, other force will come on this side. So if I extend the line of action of force, they will be collinear. So there was no contribution of the forces from BC and AD. The resultant is 0, though the resultant of this two, so resultant force on the torque is 0. The resultant force on the coil is 0. But this will behave like a couple or it will behave like a dipole. So this is the situation. Now if there is sine theta, the relation should be a cross product. So the coil rotated in an anti-clockwise direction, M was downward, M is moving towards B, M is moving towards B. So your formula should be tau is equal to N cross B, similar to tau was equal to P cross E. So here the M vector was moving towards the magnetic field. So the relation should be M cross B. So this is the situation. This is your general formula. If we have a n turns, we multiply it by n also. So here if I have a n turns, I will write M vector is equal to Ni A vector. So tau is equal to M cross B. Now if this keep on rotating, see there was the cases stable equilibrium normal position. So we know that when the torque acting is 0, that is a stable position or a normal position. So when this coil start rotating, earlier angle is 90, sin 90 is maximum. So maximum torque act on it. Now it start rotating. Theta decreases. At this point, the magnetic moment and B are in the same direction. Torque becomes 0. So this is the stable position. Again, so I can say the situation if M vector is parallel to B, that is theta is equal to 0, or it is an anti-parallel, say theta is equal to 180 degree, tau is equal to 0. The resultant force always remains, the resultant force always remains 0. The resultant force always remains 0. Torque is non-zero, but this is a stable position, same as the case of electric dipole. So if M is parallel or anti-parallel, the torque is 0. If it is 90 degree, that is the torque is maximum, so MB sin theta sin 90 is 1. And if it is 180 degree, we know it is an unstable position of a dipole. So this is the torque acting on a rectangular loop in the uniform magnetic field. So we wind up our lecture with this topic, torque acting on a rectangular loop. Remember, it is similar to an electric dipole placed in uniform electric field. You see the relation between them. Have a nice day.